a 10 kilogram crate is being pulled to the right across a frictionless surface, or we got wheels on there, and starts off going 2 meters per second. We're going to pull on it. It's going to move 10 meters in 3 seconds. So we want to know what's the acceleration on the crate, and what is this applied force right here. And so let's go ahead and solve it. Well, to find the acceleration, I'm given kinematic information. So I'll use the kinematic equations like we did in Unit 2. I have to look at what I'm given: initial velocity, displacement, and time. I'm trying to find acceleration. Notice that I'm not given the final velocity, and I'm not trying to find it. So that means I would use the equation that doesn't have final velocity in it, which is the third one on your list, which is delta x equals v naught t plus 1/2 a t squared. So what I'm going to do, now this is just my habit. I usually solve for the unknown before I plug in any numbers. Usually that saves me a little bit of writing. In this problem, it might not. So if you plugged in the numbers first and then solve for the for acceleration, that's fine. That's just not the way I do it. So first thing I'm going to do is subtract this to the other side. So this is going to be delta x minus v naught t equals 1/2 a t squared. And now I'm going to solve for a. So a equals 2 times delta x minus v naught t over t squared. And this is usually what physicists do. Physicists don't even like to plug in numbers ever. In fact, I took a class at Fresno State, upper division mechanics class, and 2 semesters, 105A and 105B. We used a calculator for one problem the whole year. Everything was about figuring out the expressions. And so when we did have that, when we did get a problem where we had to use a calculator, we were all outraged, like, why ruin our perfect record? But anyway, let's figure this out. This is 2 times delta x was given to be 10 meters minus 2 meters per second times 3 seconds, all over 3 seconds squared. I don't know if I can do this without a calculator or not. Let's see. Let's try to do it without a calculator. This becomes 4. 2 times 4 is 8. So this is 8 meters on the top over 9 seconds squared. And what is 8 divided by 9? Did I do that right? Yeah. 0.88? And that's my answer. That's the way I would do it, but probably most of you plugged in the numbers first and then arranged it. That's okay. Just be real careful. Use units to make sure you're not messing it up. All right, now I'm going to find the applied force. Now, of course, you can just go directly to Newton's second law, but I'm going to do something that is a little bit more elaborate, just because I want to demonstrate what you learned about last night when you watched the video on the procedure. I'm going to use the procedure to do this problem, even though it's probably a little bit much. It's a little overdoing it. The first thing you do when you use the first step of the procedure is to write down what's given, read the problem and write down what's given, what you're trying to find, and then solve it, and then draw kind of a diagram of the picture. So basically we started with step 1 of the procedure. The next thing you do, step 2 of the procedure, is to draw the free body diagram of the object of interest. Okay, now, so here's my object of interest. I'm going to draw it all by itself. You can put the wheels there if you want. And then what I draw are the forces acting on that object. What are all the outside forces acting on the object? Well, even though it's not drawn here, obviously we have gravity, the weight of the object, the mass of the object times g. And then we have a normal force, which I'm going to just draw with one force. Of course, it has 4 wheels probably, and they're each supporting a fourth of the weight of the crate probably. But we don't bother with that. We just draw it with one arrow. And that's the force between those two surfaces pressed together. And it's perpendicular to the plane, so we call that the normal force, because the word normal means perpendicular. And then we have this applied force. Okay. Now I'm going to do step 3. I'm going to define my x and y directions. And as I said, on most of the problems that we're going to do, the x and y axis are going to be pretty much always like this. But in the next unit, we're going to be doing inclined plane problems. That is, we're going to roll down a hill. And when you roll down a hill, you tilt your x-y axis to match the hill. And there are other problems where you change the x-y axis to match the problem you're trying to solve to make it easier to solve. So I don't skip. I'm trying to get you in the habit of using it, so I don't skip step 3. Now we can go to step 4, which says use Newton's second law in the x direction and in the y direction to solve your problem. Now, in the y direction, we don't really need to, at least not yet. The normal force will be equal to the weight. I think that's pretty easy to see there. But in the x direction, well, if I sum the forces in the x direction, that will be equal to ma in the x direction. But then I look and I say, hey, there's only one force in the x direction. So that's my applied force. Therefore, that applied force is the net force. So it's going to be equal to ma. And I know what m is, it's given, and I know what a is. I solved it in part A of the problem. So the applied force is just going to be 10 kilograms times 8 or 0.88 meters per second squared. And so that's going to be 8.8 newtons. Okay? So let's zoom out so we can see everything here. I'm already zoomed out. Okay. So this is a fairly easy problem. We're going to, most of the problems you're going to work are going to have more forces involved in this, but it kind of shows you kind of the map of how we're going to approach all these problems. You're going to, sometimes you're going to be given kinematic information to solve for acceleration, and then you use that acceleration to figure out what the forces are. Sometimes it's going to be the reverse. You're going to be given forces to solve for the acceleration, and then you might have to use that acceleration to solve kinematic problems. But it allows us, and this is pretty boring, okay? I mean, I can dress it up. I can, you know, make this a funny thing, and I can put a cat on the street, and like, or I don't know. But this really, this basic kind of stuff that we're solving right now is the foundation of all the technology that we use. I mean, mechanical engineering, civil engineering, all the stuff that we do, it starts from, I mean, this is the basic foundation of all that stuff. So it's kind of, look, these problems are not all that exciting. They're really not all that inherently interesting, except that, wow, are they important. And they lead to places where you may want to go as a career, where you can solve problems that are really important. And lucrative, I might add. Anyway, that's all.